Okay.
All right. Hello, everybody, and welcome to our Mountain Talk with Professor Joshua Pepper from Lehigh here. I'm so glad you could all be here. Today's presentation is going to go for about a half an hour, and Joshua is going to talk for about 5 minutes and give us an overview of what he's been working on, and then we'll ask you to chime in with your questions. The way you can do that is typing in the bottom of your screen, bottom right-hand corner, you can see a chat box, and just type your question in there and I will read it so that he doesn't need to be squinting at the screen at the same time thinking of how to answer your questions. Without further ado, let's turn it over to Josh and let us know what you've been doing.
All right. Thank you very much, Jennifer. It's great to be here. And what I'll be telling everyone about today are some of the new discoveries that have come out of our research project that we're doing here at Lehigh in collaboration with a few other universities. I'm an astronomer, and my specific field is the discovery of extrasolar planets, planets that orbit nearby stars. And the way that we do this is that I'm part of a collaboration that involves about a dozen different universities all over the world. That's mostly led by Lehigh, Vanderbilt, and Ohio State universities. And what we do is we use robotic telescopes. One is in Arizona and the other is in South Africa to scan the sky, observing millions of stars over many, many years. And what we're looking for is a case where a star is dimming by just a little bit regularly, about every few days or so. And that can be caused by, among other things, a planet that's orbiting the star along our line of sight. So this is a method that we can use for discovering planets orbiting these stars. And the value of doing this is because we're trying to understand more about how planets form and evolve and what kind of planets are out there. And the recent discoveries that we've made are of a pair of planets that are called KEL-9b and KEL-11b. And the word KELT that's the name of our telescopes. Those are the kilodegree extremely little telescopes, and I can explain why we named them that if anyone wants to know. And so the planets that are named after them are especially valuable scientifically because although there are thousands of planets that are known around other stars, they can be more or less understood based on their overall properties. And these particular planets are really exciting because they are orbiting very bright stars as seen from Earth, which allows us to make a lot of very precise measurements of the properties of these planets. And it also allows us to do a lot further follow-up and observation with other telescopes, like the Hubble Space Telescope or the Spitzer Space Telescope or the upcoming James Webb Space Telescope that's going to launch in a couple years. And so we're very excited about this because these planets will allow us to really probe the extremes of how planets can live and exist, as well as measuring their atmospheres, giving us the tools to eventually start searching for life on other worlds, even though we're not expecting to find life on these particular ones, for reasons that I can explain later. So that's the basic idea. We've made these great discoveries. KEL-11 was published about a month and a half ago in the Astronomical Journal, and KEL-9 was published just a few weeks ago in Nature. And I think, although I didn't get the copy of it now, the most recent edition of Nature just came out and we got the cover of the magazine. And so I wish I could have shown the copy here. I think it's going to arrive in our mailbox in about an hour. But you can go, anyone can go online if you just go to Nature, I think it's naturemagazine.com or nature.com, and see a picture of our planet on the current issue, or an artist's rendition of our current planet on the current issue. So we're very excited about this, and I'd be happy to take any questions about any aspect of this research.
All right. So again, everybody, down on the lower right hand of your screen is where you'll type your questions. And while you're thinking about those questions, I had a few for you. So there's KEL-11b and KEL-9b.
Yep.
What makes each of those special?
So the way that we talk about them is that KEL-11b we've been affectionately calling the Styrofoam Planet. Both of these planets are gas giant planets. They're like Jupiter and Saturn in our solar system. They're big balls of gas, almost entirely hydrogen. But these particular planets are are hot Jupiters because they orbit very, very close to their host stars. They orbit so close that KEL-11b goes around its star once every 4.5 days, and KEL-9b goes around its star about once every 1.5 days. And in comparison, Mercury, the closest planet to our sun in our solar system, takes 88 days to go around. So these planets are really, really close to their host star, and they're gas giants. KEL-11b we call the Styrofoam Planet because of its low density. It is really, really puffed up, like a small number of other planets that are known. Basically, it has 20% of the mass of Jupiter, but is 40% larger. So it's so low density, it's got the equivalent density of styrofoam. So that's why we call that the Styrofoam Planet. And KEL-9b is very exciting because it is the hottest planet ever found. Its host star is incredibly hot, and the planet itself is orbiting so close to the star that it gets more irradiation than any known planet, and therefore its surface, the upper layers of its atmosphere, are incredibly hot. And that helps us probe the extremes of how hot can a planet live in such an environment.
Great. We have a couple questions about that. So Tom Hoffaker is asking, does the KEL telescope detect planets around dim M-type stars as well as brighter OB-type stars?
Great question. So the answer is we have the ability to probe a small number of M-type stars, and for everyone to realize, M stars are the class of stars that are a lot smaller, redder, and dimmer than our sun. But they're very exciting because they're the most common kind of star in the universe, and any planets orbiting them really close could still be in the habitable zone of those stars. KEL probes a small number of M dwarfs, but those are the brightest M dwarfs in the sky. Because our telescope is so small, we simply don't have the power to really measure M dwarfs as precisely as other telescopes. But we do have the ability to measure OMB type stars, and those are the opposite. Those are much hotter, brighter, and bluer than our sun. And so we do measure those stars. We generally can't find planets around the OMB type stars because of the size of those stars. Those stars are so large that the equivalent dimming by a given planet is so small that we can't detect it. So really what we do, if you're familiar with star types, is that we are most sensitive to planets around A and F type stars, which are stars about anywhere from a few hundred to a few thousand degrees hotter than our sun.
Well, Austin Nielsen's question is, do you know anything about the mass of the host star in comparison to our sun?
That's right. In both these cases, we know the masses of the host stars. In the case of KEL-9b, the one that's orbiting the really hot star, that's an A-type star, and that star is about 2.5 times the mass of our sun and about 10,000 degrees Kelvin. KEL-9 is orbiting a G-type star, a bit closer to our sun. The star is about 5,300 degrees, just a little bit cooler than our sun. 300 degrees Kelvin, and the mass is about a little over 40% larger than our sun. And that's because KEL-11b's star is a little bit evolved. It started to exhaust its nuclear fuel, and it started to swell up on its way to becoming a red giant. And we know the masses of these stars because of what we call the Wobble technique, of the radial velocity method of seeing the gravity of the planets tug the stars back and forth. And because of the amount of tugging, we can tell how massive both the stars and the planets are.
Katrina Branting, class of 80, says, do these planets have any moons?
Oh, it would be awesome to find moons around these. These particular planets probably don't have moons just because of how close they're orbiting to their host stars. Because, again, they're orbiting so close, they go around these stars every few days. And at that proximity to their stars, the moons would probably not have a stable orbit to orbit in. Basically, they'd be tidally torn away from their stars, so they couldn't stay in orbit. If these planets, though, were a lot further away from their stars, orbiting, say, around the distance that Earth is from our sun, then there would be no problem to have moons. But detecting moons is really hard. It's really pushing our limits to find a lot of these planets, and detecting moons is that much harder because they're smaller and less massive.
And why would it be awesome to find moons? Is there a thing in your field?
There's a lot of excitement about finding moons. One thing is that if you find moons around a planet, that tells you something about the planet's formation. Because certain methods of forming planets would yield more and more massive moons, and others would not yield any moons or much smaller ones. But the other really exciting thing is we would love to know if there are gas giant planets, like the two KEL planets we found, but if they're orbiting a lot further away from their host stars, then although the planets couldn't be habitable, their moons might be. And so you could have a terrestrial size moon, a moon that's the size of the larger Jupiter moons, that could actually be in the habitable zone of its star, even though it's orbiting its own gas giant planet. And so we'd love to find those.
Okay, D. Chapley asks, what part of the spectrum do you search to find these planets? Visible, infrared, UV, or other?
So the method that we're using is the transit method, where we're looking at the planet going in front of the star, and so we're observing in the optical. We're observing in the optical, a little bit into the slight infrared, but mostly in the optical bandpass. And we also do the same analysis with the radial velocity measurements. The Wobble measurements that we make are mostly in the optical. We do use some infrared measurements to see how whether we can see the reflected light of the planets. And we use the Spitzer Space Telescope to do that with KEL-11b, and we found that, which was beautiful. We generally don't use ultraviolet. There aren't a lot of ultraviolet telescopes available anymore these days. So, yeah.
Tom has another question. How many light years away can the KEL telescope detect planets?
So the KEL telescope is able to observe planets around stars that are just a little bit fainter than can be seen with the naked eye. Because we're really focused on bright stars, we tend to find planets around stars that are roughly between a couple hundred to 1,000 light years away. That's still our little portion of the Milky Way galaxy, but that's the distance that KEL detects planets. If we could measure M-dwarf stars a lot better, then we could find planets even closer. But most of the stars that we're observing are a little bit further away than that.
Katrina has another question. How many planets are known in the universe? I guess we should say in our universe.
Right. So we've basically gotten direct confirmation of something like 2,500 to 3,000 planets. And when I say confirmed, what I mean is we've seen the initial signatures of the planets using one of a number of methods, and we've made enough follow-up observations to be absolutely certain that the thing that's causing those signatures is the size and or mass of a planet. Now, we can extrapolate from the number of stars that we've searched for planets and the number of planets that we've found to estimate how common planets are. And based on those estimates, we expect that there is something like 1 to 3 planets out there for every star in our Milky Way galaxy. So if we've got 200 billion stars in our Milky Way galaxy, then there's something around 500 billion to 1 trillion planets in the Milky Way. Those are the estimates. They'll get better sooner.
Wow. And what do you have to do to get a planet named after you?
So the question about naming. So the convention right now is that planets are named after the telescope that discovers them if they're found using the transit method. And if they're found using other methods, then they're named after the existing catalog name of the star. And this is just a convention that's grown up. So because our telescope is called KELT, the first planet we found was called KEL-11b, because you always name a planet with a lowercase Latin letter like B, C, or D after the star that it's named. So the stars technically are called KEL-11 and KEL-9, and the planets are KEL-11b and KEL-9b. Now, when we discover additional planets in the system, they're called C, D, or E. So KEL-6 was a planet that we found. We found KEL-6b, and then later on, people found KEL-6c in the same solar system. The official organization that names planets is called the International Astronomical Union. It's the worldwide network of all astronomers. And they have recently renamed a number of the more popular or more well-known planets around other stars by a set of names that were suggested by the public. I don't know the mechanism for doing that, and those names, although official, have not been widely adopted, because as astronomers, we have to use whatever names are most convenient and useful for communicating what we're finding. So we generally don't get to name planets after people. The one exception is minor planets, which are asteroids. Those can be named after living people, I'm pretty sure. They certainly have been named after dead people. And there's actually an asteroid Lehi that was discovered back in the early 20th century. So there is a planet Lehi out there that's technically a minor planet.
Wow. I was thinking that International Association could accept gifts. And the largest donor gets their name on a banner.
There has been a lot of discussion about ways of raising money. So far, they're not auctioning off planets, but well, we'll see.
All right, Joe Fedak from class of 91 has a question. You mentioned the acronym KELT.
Yes.
And I love that it's nothing really super scientific. Can you repeat that and tell us how that came
So
about?
only the first word is a little bit scientific. So KELT, K-E-L-T, stands for the Kilodegree Extremely Little Telescope. So the reason it's named that is, so kilodegree, what that means, kilo for 1,000, and degree is just an area on the sky. So KELT, in a single shot, observes an area on the sky of about 1,000 square degrees, which is much, much larger than most telescopes. Because we're a small telescope, we've got a very wide field of view, and so we can observe a lot of the sky at once. And that was the sort of characteristic, the defining characteristic of our telescope. So that's why we called it that. One of the other reasons we chose that name is because at the time, and to this day, astronomers love to name their telescopes after how large they are. So there's places like the VLT, the Very Large Telescope, the GMT, the Giant Magellan Telescope, the EELT, the European Extremely Large Telescope. So about 15 years ago, when we started the KELT project, there was a plan to build a project called CELT, which was the California Extremely Large Telescope, and we thought we would just swoop in and steal the KELT acronym.
Nice. How little is it?
So the aperture of the telescope, the width of this lens is just about 2 inches. It's 4.5 centimeters. So that's a very small aperture, and that's only necessary because we're looking at very bright stars. So if you're looking at bright stars, you don't need a huge aperture or a huge light collecting area the way you would for observing distant galaxies or supernovas.
Oh, and how big is can you carry it home and work from home?
You could. Actually, I have carried the KELT North telescope. The whole telescope is maybe the height of a person, but it sits on a pier that's about 3 feet tall. So the whole telescope is maybe about the size of a person's torso, and it weighs about 55 or 60 pounds.
And I'll ask Richard Bell's question next. Where is it?
So there's the two telescopes. KELT North is in Arizona at a little observatory called Weiner Observatory, which is in the extreme southeast portion of the state, southeast of Tucson. And KELT South is in Sutherland, South Africa. So South Africa is one of the best places in the southern hemisphere to observe the sky. And Sutherland is a little town, tiny little town, about a 6-hour drive north of Cape Town, South Africa.
And you go there often, I think?
I did go there often as when I was a postdoc setting up a telescope. Now that I'm a professor, I get to send grad students there.
Austin's question is, are these planets located in any of the constellations?
Yes. So every area on the sky is technically encompassed within a constellation. KELT-11 is in, I believe, the constellation Sextans. It's a southern telescope. It's a southern constellation, and KELT-9 is in, I think it's Andromeda, but I'd have to double check.
Okay. That's almost a stump the chump question.
Yes.
All right, Kelly Kreibel, 93's question is, what, if any, criteria do you have that inform you as to the probability that a particular star may have planets? Are there fertile regions of star clusters that may be better than others?
Great, yeah. So there's a lot of debate about this, about what kinds of stars are more or less likely to have planets. And there's a few things that we found out, but we're still trying to learn a lot more. One thing we know, and this is a result of the NASA Kepler telescope that has been working for about the past 5 or 6 years. We know that M dwarfs, these dim red faint stars, are very likely to have planets. They're probably more likely than yellow or blue stars like our sun or hotter stars to have planets. We also know that stars that who have a lot of signatures of metals in their atmosphere, and when astronomers say metals, we mean anything heavier than helium. Basically, these are stars whose initial composition had a little bit more of the other stuff that makes up the universe. We know that they're a lot more likely to have giant planets. But aside from that, we don't have a very clear sense of why it is that some stars are more likely than others to have planets. And that's one of the major areas that are under investigation in astronomy. but we'd love to be able to identify planets that are more or less likely to have stars. But aside from metal-rich stars or M dwarfs, we still think though that almost all stars do have planets. We're at the point now where on average a star is probably more likely to have planets than not. And so it really all comes down to around which stars is it easier for us to detect the planets that might be there.
And so a guest, unless that's somebody's first name, which would be cool. What are the criteria for being habitable, and what percentage of the planets being found are habitable?
So another area of intense debate right now. The classic idea is that a planet has to be in the habitable zone to be habitable. And of course, what that means is the planet has to be the right distance from the star in its orbit, so that the temperature of the planet, due to the heat of the star, is such that liquid water could exist on the surface if there were a solid surface and if there were an atmosphere to provide pressure. So if you've got a rocky planet like the Earth that is orbiting at the right distance from the star for there to be liquid water, that's how we classically define habitable. It is a very crude definition and also very incomplete, and that is widely recognized. And so there's a lot of debate right now in astronomy about just what are the extremes of how close or how far from the star, or even other completely different scenarios where you could have life. And so people are working on that. Of the 3,000 or so planets found, only a couple dozen are believed to be reliably habitable in the sense of being that right distance from the star. But that's mostly because the difficulty of discovering planets as far away from their stars as the habitable zone is. So we think that number is going to increase a lot more.
Exciting. So Joe is asking, is there any specific place online we can find info on the telescopes?
We are in the process of migrating over some very old and out-of-date websites to a new website, which should hopefully be live in about 2 to 3 weeks. If you search right now, you can find on the websites for both KEL North and KEL South. If you just Google KEL North and KEL South, you'll find the existing websites at Ohio State and Vanderbilt for those two telescopes. But they are, as I said, they're old and not well maintained, and we are in the process of building a new website. I hope that we'll be able to distribute an updated version of that link soon.
Okay, yes, we will do. Isn't it funny that you can discover new planets and yet getting a website updated is...
That is, I have skills. Web development is not one of them. We'd love to have more people who can help us with that.
Katrina's question is, what's the next new technology for finding stars and planets?
So the next big one that's coming up, not soon, but in the next, say, 7 or 8 years, is that the methods that I've described so far are the transit method and the wobble method. So transit, you look for a fortuitously inclined planet's orbit and look for the planet passing in front of the star, or you look for the wobble of the star due to the gravity of the planet. Those are the main methods that have been used so far. In about 2025 or so, we expect to launch the next big NASA observatory called WFIRST. And that is going to be a space telescope that will search for planets using a totally different method called microlensing, where you look for how the gravity of an intervening star bends the light coming from a background star, and if that intervening star has a planet around it, that changes the lensing and the bending of that light. This is general relativity, the same kind of science that Einstein developed that describes how space bends light and matter. And so that telescope, which will launch sometime in the mid-2020s, we think will discover tens of thousands of planets, including lots and lots of planets in their habitable zones. So that's the next big method that we're very, very excited about.
Nice. I love how Lehigh alumni are like, yeah, this is nice, but what's the next one? Well, and speaking of that, what is it that, what's next for your work now that you've found the Styrofoam Planet?
So we are going to keep the KEL telescopes going for the next couple of years because they're yielding great results, and some of these are planets that are fantastic to find as soon as possible, because a lot of the big telescopes that we have for investigating their detailed properties, like Hubble and Spitzer, have been around for a while, and they're not going to last forever. So we want to find as many planets as possible to make use of all the resources and telescopes we have for investigating them. After that, I'm part of the science team for another NASA mission called TESS, TESS, which is the Transiting Exoplanet Survey Satellite. That is a space telescope run by MIT, which will be launching in just about a year from now. And that is going to do this kind of transiting planet detection over the entire sky, sort of as the successor to the NASA Kepler mission. And TESS is going to be a key focus of my work for the next 5-10 years after that.
So you've mentioned a bunch of other universities as you're talking. Is your community more collaborative, more competitive? Is there a space race?
There is both of those going on. So there is definitely a race between different groups to find planets, because it's exciting to find them, and the sooner you can find them, the more you can learn about them, and we all want to learn the most as we can to understand them. But there's a very collaborative environment. In fact, in a week and a half, we are doing a joint announcement of another planet called KEL-11b, which will be coming out, I think, the 5th of July, in collaboration with a European survey that found it at just about the same time. And when we found out that both they and us had discovered it and were preparing to announce it, we decided to not work together, but we're going to make our announcement at the same time, so that we're not, rushing each other or trying to cut corners on the discovery. So that kind of thing happens sometimes in science. Yeah.
So did you just tell us a super top secret?
It's not super top secret, and I don't think you're not going to be able to use that information to go out and find the planet yourself. So, so I'm not worried about being scooped on that front.
I'm going to go trademark it. So Austin has a question. Any good books on exoplanets that you could recommend?
Oh boy. It depends if you're a student, or if you're interested in learning about the details of planets, then a great book that I actually use to teach in my classes is called How to Find a Habitable Planet. And that's by Jim Casting, who's a professor over at Penn State University. And it does a little bit of math and a little bit of chemistry, but it's anything that anyone who's in college or who has taken a class or two in math or physics should be able to grasp. And it talks all about the process of finding planets, about habitability, and all these questions. And I think it's written really well.
That's great. So we have time for one more question, and I don't see any on the chat, so I'm going to ask, what brought you to Lehigh, and what makes you stay?
So
besides great opportunities like webinars.
Absolutely. So what brought me to Lehigh was that I was finishing up my postdoc, and I found out about the Lehigh opening for a professor in the physics department. And I actually have a family connection to Lehigh. My father, Stephen Pepper, was class of 1959. He graduated from Lehigh way back in the day when it was a very different institution, all male, all engineering. Bethlehem, I think, was a very different place. And so I knew about the university and heard about its reputation. And I got a great time visiting the campus, visiting the physics department, and meeting everyone here. And it just seems like an incredibly supportive and positive environment with really high-quality students here for doing the kind of student research that I love to do.
Wow, great. And you stay because...
And I stay because Bethlehem is a beautiful place to live. I love it here. My wife loves it here, and we've been having a great time. And the campus is gorgeous, and it's just been a wonderful place for us to be.
Nice. One of the last questions I almost always ask our webinar participants, and it's sort of a pun for you, is what keeps you up at night? And obviously, everything keeps you up at night.
Everything, yeah.
In your field, what is the thing that you worry about?
So what do I worry about? I guess I worry about, honestly, the thing that worries me the most is the declining funding for basic scientific research. There are, budgetary issues that we all know about. But my field, astronomy, is funded something like 90% by the federal government, and that's where we get our funding through NASA and the National Science Foundation. And whenever the government budget drops, the budget for those agencies drops as well. And so all of astronomy gets less than 0.1% of the federal budget. But when there are drops, even of a small portion of that amount, that hurts our ability to build telescopes, to build new instruments, to train students. And so what worries me is long-term declining investment in basic research.
Okay. Well, on that note, it is 12:30 exactly, and we will be sending out a note after this with links to some of the things that we talked about today, including the cover, which is amazing.
Yep.
Congratulations on that.
Thank you.
And additional information on upcoming webinars. So you'll also see a survey after you close down this screen. You'll see a survey pop up. We hope that you'll take that because we just started doing these a few months ago, and we would